Alright, hello everybody. This is the projectile motion notes moving in 2 dimensions. The purpose of these notes are to kind of finalize everything that we learned in that Trace That Trajectory lab, and make sure we understood all the concepts that we were supposed to, so we can move on to the next step in our unit. Okay, so in that lab, we analyzed this, simply that ball rolling off the table and falling to the ground. Now technically this is a projectile. It's an object that was launched from the table horizontally and it fell to the ground from there. So obviously it went to the right, it went down. What we saw when we studied this is we graphed the horizontal motion, we graphed the vertical motion, and we saw that the two were completely independent of each other. One did not affect the other. So to understand why that was the case, let's look at the ball when it's right here, in the middle of its motion. One of your questions on your lab was to give a force diagram of the ball mid-air. So let's do that right now. Let me pick red here. And we're going to make a force diagram over here on the left of the ball. So there's the dot, there's our receiver. We have to think about the forces acting on the ball. We should all know by now that the first one you should do is gravity. So gravity acts straight downward. Label that Fg. Okay, there's one force acting on the ball. As I was walking around and looking at your papers, I saw a lot of people add another force to the right. And most people labeled that force applied. Okay, here's the deal. Yes, at some point there was an applied force to get this ball moving to the right. Because obviously there's probably someone over here off screen that rolled the ball across the table and which made it fall to the ground. However, at this point right here, maybe it's just me, but I don't see a guy pushing this ball to the right at all. The force that was applied to get this ball moving happened way in the past. At this moment, when it's mid-air, it should only be the force of gravity that's acting on the ball. So that's it. That is your force diagram. It's just that force of gravity. Okay, since we just have that one force acting on the ball's forces are unbalanced, meaning there's a net force acting on the ball. The net force is the force of gravity. That downward net force causes the ball to accelerate in that downward direction. Anytime you have a net force, it's going to cause something to accelerate. If you look, there's no force left or right. Some people included the force of friction due to air resistance. It's so small in this low velocity, low time example that I wouldn't even include it on the diagram. So since we have no force to the left or right to push or pull it, the horizontal motion was not affected at all. Horizontally, the motion of the ball remained constant. Okay, let's look at some graphs. So this graph is very similar to what we did in the lab, except we're looking at the horizontal position of this object and the vertical position on the same exact graph. So once again, this is a projectile launched horizontally, except each dot's going to represent, looks like 1/10 of a second, and the positions on the axis are actually the positions in the horizontal and vertical direction. Okay, in these spaces provided on your paper for your notes, I want you to make a motion diagram in the horizontal direction and the vertical direction. To do that, you're going to place a dot vertically for each of these positions. So right above that first dot in this box, we're going to place another one. Right above this one, place another one. And right above that one. And so on and so forth. And also for the vertical, we'll do the same thing, only directly to the left. So for the first dot, we're going to place a dot here. Second dot, it's not very farther down than that. Maybe a little bit more, a little bit further. Mine are so close together because I made big dots. Okay. Once you get that all done, connect them with arrows, and you should end up with something kind of like this. So if we look at this horizontal direction, you can see that the space between the dots is constant. However, as the ball is dropping, what we see is that these dots start to spread out, and the distance between the dots is increasing. So this kind of proves what we've seen already in our lab, that the projectile has this constant velocity as it moves to the right horizontally, but it has this accelerated motion as it moves downward in the vertical direction. Okay, the next thing we're going to look at is a ball that's simply being dropped and a ball that's being launched horizontally. And we're looking at how the two compare. Okay, so when you look at this, we're going to do the same thing. We're going to look at the vertical position of each of these, the horizontal position of each of these, and look at the motion diagrams. So you'll see this diagram on your paper as well. What you can see is that vertically, they all line up really nicely. Horizontally, the ball that was dropped only has that single dot. However, it has a circle around it. The one that was launched horizontally has that constant velocity as it goes to the right. There are a couple questions in your notes that ask you about this diagram right here. The first, why are the motion diagrams shown in the vertical positions the same? So why do those line up so nicely? And the second, why is there only one dot for the ball being dropped on the horizontal motion diagram? Why aren't there multiple yellow dots going to the right? Questions for you to answer and think about. Okay, our last diagram we're going to look at, an even more complicated one, and this one it really helps to see it in color on this video, because on your paper it's hard to tell. What we have are three different balls, but each have the same mass. Okay, so there's the yellow ball that's being dropped straight down, the blue ball that's being launched horizontally at a speed of 2 meters per second, and the gray ball that's also being launched horizontally, but at a speed of 3 meters per second. Okay, so as we can see, vertically, once again, they all line up very nicely. And that might have to do something with the acceleration of gravity. Now, to the right, we have three different horizontal motion diagrams. The first, just a single dot for the ball that's being dropped. The second, they're evenly spaced as they go to the right. And for the gray ball, they're also evenly spaced, but they're a little bit more spread out than the blue ball was. The question that you have is that if it's the same force acting on all three of these balls, then why do we have separate motion diagrams in the horizontal direction? Think about that question, answer all of these questions on this back side, fill in the blanks on the front, and then you're ready for your Socrative quiz.